As mentioned, I'm George Montañez. This is collaborative work with my students, Julius Law, Dominique Macias, Akshay Krika, and Julia Vendemiati. So I'm an assistant professor of computer science at Harvey Mudd College, and my training is in computer science and machine learning. And so in life, we're often told that we should be bold, right? That we should be confident. And on the other hand, we're also told that we should be responsive and adaptable to situations. And what I want to convince you of today is that those two goals are actually in tension, they're in conflict. So our work looking at this issue of bias versus flexibility or expressivity is built on what is called the algorithmic search framework, which is a view of machine learning as a type of search. And we, using that view of search, we're actually able to look at many different types of learning simultaneously. So things like classification, regression, unsupervised learning. It gives us a unified framework for being able to prove results. Furthermore, we build on recent work in this framework showing the need for certain types of biases in learning processes, right? In this paper, we prove that an algorithm cannot simultaneously be highly biased and also very flexible or expressive, meaning that it adapts or changes readily to changes in the training data. We give bounds for expressivity in terms of the bias, and we bound bias in terms of expressivity. And this leads to a trade-off, that for an algorithm that has preferences towards certain outcomes, very strong preferences, it cannot be flexible, and vice versa. Okay, so we're going to start by giving some background about the algorithmic search framework. So in 1982, Tom Mitchell wrote a paper entitled Generalization is Search, where he was looking at what he called concept generalization, which nowadays we refer to as binary classification. And he said that you imagine you have an instance space where you're trying to label some subset of instances as positive instances. And he said that basically you have a hypothesis space, which are all the possible labelings of the instances in your space. And you are essentially selecting out a subset of instances to label as positive. So you can imagine that hypothesis H1 selects out this group of points to label as positive, and the remainder are all negative. Whereas hypothesis H2 selects out these 3 points as the positive instances, and maybe H3 just selects out a single point as a positive instance. But essentially, you are selecting out subsets, and what your learning process is doing a search in this hypothesis space. More generally, we can view a lot of different areas of machine learning as search. So you can basically think of machine learning as a search through a parameter space. And this will apply to things like classification, so not just binary classification like Mitchell looked at, but also multi-class classification, regression, clustering, which is a type of unsupervised learning, parameter estimation, and also hyperparameter optimization. So what does this look like? So here are the components. We have a search algorithm, which we abstract as just some black box searcher. We have some finite discrete search space. And if the finiteness assumption troubles you, you can think that whenever you have finite representation of numbers, so you have a limited number of bits to represent a number, you're going to end up in a finite discrete situation anyway. So anything that you want to run on modern computer hardware will be under this situation. We also have some non-empty subset of the search space, which we call the target set. So these are the elements of value that your searcher is trying to find. And finally, we have an external information resource, something like a data set, which gives you clues and guides you along in your search. Okay? The algorithm itself we look at as a black box iterative process. It has access to a history of points already sampled and feedback it's already gotten from the information resource. It uses that to compute, which is represented by the gears, a probability distribution over the search space. And then from that probability distribution, it selects out the next point. And this applies both to stochastic as well as deterministic algorithms. So for a deterministic algorithm, its probability distribution is just a point mass on a single element. Okay? And so we say that a search is successful if during the course of the search, an element of the target set is found. So that is the framework within which we're working. And now let's talk about bias. So bias is just any predisposition towards certain outcomes over others, which control how your algorithm interprets data. So although data sets can certainly themselves be biased, this type of bias, this inductive bias, is the way that the algorithm responds to the data or interprets the data or extrapolates from the data. And when we talk about bias in context of AI and machine learning, typically it's with a very negative connotation, right? So we talk about biases like racism or sexism or ageism. But this talk is not about those sorts of unethical biases, right? So we're right to avoid those types of biases in our algorithm, but there's a different type of bias that we certainly need in our algorithms, and that's referred to as inductive bias. So what is inductive bias? Inductive bias is any preference for solutions or hypotheses based on something other than strict consistency with training data. So this is essentially the assumptions that are built into your algorithm. And using this, it results in some, what I think of as an inductive orientation of your algorithm, which is a vector, P bar D, which is an algorithm's expected distribution over the search space if you're selecting data sets from some generating distribution. So remember the picture that we had, if we go back to it real quick? So there's a series of distributions during any search. If you were to average those distributions together and then take the expectation of that process, you would get kind of one mega distribution, right? Like one exemplar distribution, and that is the inductive orientation of the algorithm. Okay. And so this is a result, obviously, of the algorithm's inductive bias, because however the algorithm interprets its history or what it's seen, it's going to make a different distribution. We can also view this geometrically. So because the inductive orientation is a vector, it's a point in high-dimensional Euclidean space, or a vector in space, and it has some orientation in that space. Furthermore, we could represent our target set as another vector, and to the degree that those two vectors align is to the degree that your algorithm is going to perform well. So if your assumptions are aligned with what holds in the real world, then you have good assumptions. And if not, then you're going to perform more poorly. Okay. So given that notion of inductive orientation, we can define formally the type of bias we're talking about. So for a target T, where we're representing target now as a vector, if P is the per query probability of success under uniform random sampling of your space, the bias D of T is defined as the inner product between your target set and your inductive orientation minus the baseline uniform probability, per query probability of success. Right? So this is just a linear function of your inductive orientation. And it tells you essentially what is your expected deviation in performance from uniform random sampling based on the assumptions built into your algorithm. So inductive bias, it turns out, is always needed for learning better than uniform random sampling. So there's a long history of work going back to 1980. The same Mitchell who wrote Generalization is Search wrote another paper, The Need for Biases in Learning Generalizations, where he looked at binary classification and showed that if you made no assumptions beyond consistency with training data, you would perform equivalently well to coin flipping if you were doing binary classification. And that line of work continued on until last year. We presented a paper in December entitled The Futility of Bias-Free Learning in Search, where we showed that this same phenomenon holds not just in binary classification, but it also holds for all of the problems you could represent in the algorithmic search framework, which means it's going to apply to things like regression or classification or reinforcement learning or all these other areas that we're concerned about. Okay? And we proved some results, so here is a screenshot of the paper. We proved some results in the paper such as the conservation of bias. So what this says is that if you take the set of all possible target vectors of a fixed size in your space and you compute the sum of the bias over those vectors, it's always going to equal 0, no matter what your algorithm, no matter what your data generating distribution. Which means that biases are neither inherently good nor bad. They are essentially either well-aligned or misaligned. So to the degree that you are well-aligned with some target, it means that you're also misaligned with other targets. And so essentially the takeaway is that generalization is a zero-sum game. You can't make general progress on it. You have to focus what you're trying to do. Okay. So now that we've looked at bias, let's look at expressivity. So here's a picture I like to think of for expressivity, right? So expressivity is, if we're looking at algorithms that are either flexible or inflexible, you have Adam Driver, Kylo Ren here. He's trying to give new information to the algorithm. He's trying to say it's pronounced chicken nuggets. But the algorithm is inflexible, it's biased. It always wants to be predisposed towards a certain outcome, and it just repeats its chicky nuggies, right? So it doesn't want to change or update based on this new information. That is an inflexible algorithm or an inexpressive algorithm. So informally, expressivity is how well an algorithm responds to changes in data, which means that different data sets should result in different probability distributions over your space. And a little bit more formally, expressivity is to the degree that an algorithm's expected probability distribution, so its inductive orientation, is blurred towards uniform. And so what that means is that if you can imagine that an algorithm changes its where it's pointing in space based on different training data, you would get more vectors spread across the space, so then when you average them, you would get a more uniform mega distribution, right? Okay, so we're going to use that intuition to formally define a notion of expressivity, which we refer to as entropic expressivity. So the entropic expressivity is the information-theoretic entropy of the inductive orientation vector, namely this, right? So this is just the standard Shannon entropy of a distribution, and so we take that. And so what this tells us is the more uniform the distribution, the higher the expressivity. All right. So now we have all the pieces in place, and we can look at some theorems that can be proven using these definitions. And so the first thing that we show in the paper is that we can actually bound the range of the expressivity as a function of the bias. So here we're representing bias as this epsilon, and so we can get a range that captures that. Where the left side of the range is the binary entropy of the expected per query probability of success of uniform random sampling plus the bias. And then on the right, we get this kind of gnarly expression right here, right? And so that's a little bit hard to reason about in your head. So what we do is we actually just plot some values for specific, well-known kind of exemplar values of bias. So bias, remember, it could be either positive, it could be favorable bias, or it could be negative, it could be unfavorable bias. So imagine you're maximally unfavorable, then the range is between 0 and almost the maximum entropy. K is the size of your target set, and typically we have very small target sets in very large spaces. If we didn't have small target sets in large spaces, we wouldn't spend a lot of time coming up with fancy algorithms, right? We would just uniformly random sample and be done. But typically that's the situation we're in. If we have no bias, so it's neither favorable nor unfavorable, then we are bound between the binary entropy, which is going to be between 0 and 1, and the maximum entropy on the space, which is going to be a very large number. So it's a very broad range. And if we're at maximum bias, now we're between 0 and log base 2 of the size of the target set. And remember, if you have a very small target set, this is actually going to be much smaller. So if you imagine that you had exactly one element, which was your target set, this interval would collapse to just 0. It'd be between 0 and 0, so you would have no expressivity, right? We can also prove theorems where we bound in both directions. We can upper bound the expressivity in terms of the bias, right? Where it's the log base 2 of the size of your search space minus 2 times bias squared. Or we can do the other direction. We can bound bias by the expressivity, and namely we can upper bound it by the root of 1/2 of the KL divergence between your inductive orientation and a uniform distribution on the space. So what this tells us is that to the degree that your algorithm is not uniformly placing mass on the space, it's actually concentrating mass in different areas, you can actually perform better. And in the paper, there are more theorems. I highly recommend that you read the paper. But these three that we've highlighted here, these actually tell the story, the main story of the paper, which is that while bias is needed for better than chance performance of learning algorithms, bias does hinder the flexibility by reducing how well it can respond to new data. And although algorithms that are predisposed to certain outcomes will not adapt as well as others without strong predispositions, maximally flexible algorithms are actually no better than uniform random samplers. They can perform no better. And so we proved these bounds on bias in terms of expressivity and bounds on expressivity in terms of bias, demonstrating that the trade-off exists. And we noticed that both of these, both bias and expressivity, were a function of the inductive orientation of the algorithm. And the more strongly pronounced this inductive orientation, the better you can generalize, but the less flexible you will be. And that's the takeaway message of the paper. So with that, I thank you for your attention, and I'd like to answer any questions you might have.
So, comments and questions.
Yes.
You mentioned a few, I would say, societal biases.
Yes, sir.
Have you had discussions with these people?
Yes, so mostly when people first hear, for example, the title of the paper, the Bias-Expressivity Tradeoff, they think in their head like unethical types of biases,
yes.
And this is not the case. So we are talking about just the general idea of being predisposed towards certain things, and certainly you could be predisposed towards bad things. You could be predisposed towards racism, sexism, ageism, but you don't have to be. You could be predisposed towards believing that your solutions only live in some smooth, continuous space, for example, or whatever it is your assumption is that you're making. So there's definitely a difference, and I feel a responsibility to highlight that when I give talks on this subject. This is not the type of bias we're talking about. You don't need unethical biases.
Well, I understand you quite well. So in fact, you could even have a paper in mind with the title "Biases are necessary for a correct algorithm."
Yeah.
It's a little bit challenging too much, of course, but anyway, if you give the explanation you give here, then you have the right message, of course.
Yeah, exactly.
Because they attract the attention of the people.
Yeah, so this is a provocative.
Yes, that's what I was
But
saying.
it's not intentionally provocative.
No,
I'm not the one who came up with the word bias, right?
No, I'm not. But my own mind went to that way to be as more expressive as possible, because that also includes expressivity, of course. Because you have a challenging title, then it is also a measure of expressivity.
Yes, sir.
Yes.
Okay, thank you. Other questions, comments? Still this time. Question from me. Could you show us some convincing example that is, from a large data space to some classified time space?
So, for example, how to reduce something to a search?
Today your discussion is quite mathematical.
Yes.
Abstract.
Yes.
And
So the reason why we keep it in this abstract mathematical space is because then it's easy to prove things that apply to a lot of things. But take, for example, binary classification, which was the original example we had. If you have a binary classification example, our search space is the set of all possible hypotheses or all possible labelings on your instances. Right? So if you have the people in this room, and we're trying to classify whether or not they're basketball players, all the different ways there are to label someone as a basketball player, not basketball player, would be the search space we're searching through. And we want to find the correct labeling for everyone here, so that way we're correct. Our target set is the truth, is whether or not each person is actually a basketball player. Plus, maybe we say, well, we don't have to get everyone exactly right. We can get maybe 10% of the people wrong. So it's some subset of those labelings such that they're mostly correct. And then our information resource would be some subsampling of the people where we're given the labels for them and given their features. So their height, their weight perhaps, or other physical features that we may be able to judge whether or not they're likely to be basketball players. And given that, our searcher becomes our binary classification algorithm. So if we're using something like maybe Bayes or SVM, for example. And that's how we would take a very concrete problem and cast it down to the search space. But now that we've done that, we don't necessarily have to worry about the algorithm anymore. We can just say, now we have a problem in this space, and what can we say about problems in this space? I think that's it. Thank you all for your attention.